Next, we look at the Chinese remainder theorem, and this is a very, again, classical result, and it's used to solve such systems of congruences, let's say, and it has an application, of course, in cryptography. And the problem setting is that you have a number unknown x, and you are given a set of congruences that it satisfies with respect to, let's say, n modulo basis. Here, the elementary statement of this theorem requires that the modulo values here are pairwise co-prime and obviously greater than 1. Okay, so M1, M2 relatively prime, M1, M3 relatively prime, M2, M3 relatively prime, etc., and so on. And the theorem states that this system has a unique solution under modulo M1 times M2 dot 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 up to M sub n. Okay, and the proof is not that difficult, and it's constructive, which is good because it provides us with a method to obtain the solution. Now define the number m as the product of these numbers, and we define capital M sub k as m divided by m sub k, and this is simply m1 times m2 dot 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 m times m sub k minus 1 times m sub k plus 1 dot dot up to mn. So this is simply the product. Well, you have all these numbers here. Their product gives you the number m here. And if you actually exclude one of those numbers, if you exclude m1, for instance, m2 dot 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 up to mn, you get capital M1. If you exclude m2, small m2, you get m1, m3 dot 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 up to mn, you get m2, and so on. So this is defined in this way. Now, since all small m's, m sub I, m sub j, etc., or pairwise co-prime, their GCDs are 1. This means the capital M's and the small m's, so M1, capital M1, M2, capital M2. Okay, so these numbers are all relatively prime. So if I select them and exclude them from the product, the remaining product is not going to have that factor. So if I exclude M1, small m1 from the product, I get M2 times M3 times M4 dot 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 Mn. You see, none of these numbers have a common factor with M1. So the product capital M1 is also not going to have a common factor with a small m1. Therefore, these pairs, Mi, capital Mi, are relatively prime. Okay? Simple as that. Then this means there exists since they are co-prime, the multiplicative inverse of capital M sub k under modulo small mk exists, which means there exists a yk such that capital Mk times yk is congruent to 1 modulo small mk. So yk here is simply the multiplicative inverse of the capital M sub k here. In this case, we can express the solution as this. X equals the sum from k equals 1 to n, ak times capital Mk, yk. Why is this the solution? Because observe, when j doesn't equal k, m sub j is congruent to 0 modulo mk, because small mk is a factor in capital Mj when j and k are different. You see, capital M1 includes all factors, M2, M3, M4, etc., dot, 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 up to Mn. Similarly, M sub j, capital M sub j, has all factors, M1, M2, etc., up to Mn, except for small mj. Okay, so when k is different than j, m sub k is a factor of capital M sub j, which means m sub j, capital M sub j, is congruent to 0 modulo small m sub k. So when you take, this is the number x, when you take modulo m1, for instance, all terms here that has capital M2, capital M3, capital M4, dot, 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 etc., all of them have zero contribution under modulo M1, because capital M2, capital M3, capital M4, etc., all of them are multiples of small mk, small m1 in this case. So the only term remains is this. Under modulo m sub small k, modulo small m sub k, the only term that remains is a sub k, capital M sub k, and y sub k. But under modulo m sub k, we know that this is congruent to 1. So therefore, this is congruent to a sub k modulo m sub k, which means this solution given in this form satisfies all the congruences. Okay, so this is how you solve such systems of congruences. And here, let's see an example: x congruent to 1 modulo 3, x congruent to 4 modulo 5, and x congruent to 7 modulo 8. Simply put, we would like to find a number x that gives a remainder of 1 when divided by 3, and gives a remainder of 4 when divided by 5, and gives a remainder of 7 when divided by 8. And here, just applying the solution of Chinese remainder theorem, you see the number m is the product of these, 3, 5, and 8, so it's 120. And the capital M's, capital M1 is the product of these two, that is 40. Capital M2 is the product of these two, excluding small m2, so 24. And capital M3 is the product of these two, 15. The next step, we need to find the multiplicative inverses of capital M's under modulo small m's. So find the multiplicative inverse of capital M1, 40, under modulo small m1, which is 3. Okay? So I'm not going to give how to find them, because we know we can use extended Euclidean algorithm to find the multiplicative inverses. And they are given here, 1, 4, and 7. And then at this point, you are ready to construct the solution. That is, take this one, that is A1, then take capital M1, 40, and take its multiplicative inverse under modulo small m1, which is 1. And then take A2, 4, times capital M2, 24, times its multiplicative inverse, 4, plus A3, which is 7, times capital M3, 50, times its multiplicative inverse, 7. And this solution is going to be a unique under modulo 120. Okay? Therefore, if you add them up, you get 1159 modulo 120, which is equal to 79. So all integers in the form 79 plus k times 120 satisfies this set of congruences. And 79, if you just plug it in, when you divide by 3, the remainder is 1. When we divide by 5, the remainder is 4. When you divide by 8, the remainder is 7. And 79, as I said, it's the unique solution under modulo 120. But if you add multiples of 120, the integers you get are also going to satisfy these congruences.